So well-known Taylor or Maclaurin series. That's kind of how you spell Maclaurin? Yeah, okay. Um, and importantly, they're intervals of convergence. I'm just going to kind of list them off in the order that I remember them because that's probably the order that they're most important in, to be honest, because that's how often you use them. So, number one, e to the x. It's your champion Taylor series. It's the one you want to know. It's the sum from n equals 0 to infinity of x to the n over n factorial. I do think it's worth remembering it as actually the first few terms. So like I think it's worth saying, yeah, this is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on and so on and so on. And it converges everywhere, which is great. So its interval of convergence is all real numbers. So that means that for any choice of x, e to the something will always be equal to this infinite sum. It's weird that that's showing up down there. I don't like that. Go away. Why are you there? Yeah. Sometimes that's there. Okay. The next two, I feel like kind of go with e to the x. So the next two are sine and cosine. So sine of x is equal to, I'll be honest, I like writing this one, the terms first, because I remember the terms better than I remember the pattern. So sine of x, is it an even or an odd function? Ooh, I know it's been a minute. It's an odd function, right? If you think about how sine looks, it's got rotational symmetry, right? If you rotate it 180 degrees, it looks the same. I use that to remember what sine looks like for the Taylor series, because if sine of x is odd, it better be a polynomial with only odd powers. So sine of x is looking like x to the first over 1 minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on and so on and so on. If we want to write that in the compact notation, oh, I forgot to turn off the lights on the right hand side. Let me make this easier for you all to see the polygons. Much better. So writing this in the compact form always feels like kind of a pain. It's the sum from n equals 0 to infinity, and you want all the odd powers, so you want 2 times your n plus 1 or minus 1, either way. So we want x to the 2n plus 1 divided by the same number factorial. And then we also have to make it alternate. So we want a negative 1 to the nth power. This one also converges everywhere. So it's also convergent on the interval from negative infinity to infinity. Interesting fact, if you knew this one, you could differentiate every term to get cosine. The derivative of sine is cosine. And the derivative of x is 1. The derivative of x cubed is 3x squared. The 3's cancel to leave you with an x squared over 2 factorial. The derivative of x to the fifth is 5x to the fourth. The 5's cancel to leave you with an x to the fourth over 4 factorial, and so on and so on. I think of it as the same pattern, just you have the even powers instead of the odd powers. And yes, that first term, even though I don't want to write it, it is x to an even power. I don't think anyone should write this, but technically that term there is really x to the 0 divided by 0 factorial. X to the 0 is 1, and 0 factorial is also defined to be equal to 1. Kind of weird, but true. So here we can write this one as the sum from n equals 0 to infinity of x to the 2n over 2n factorial times negative 1 to the n. And it's also convergent on the entire real number line. Here's why I group these together, because I really look at e to the x as kind of having sine and cosine, right? If you make all the terms of sine positive and all the terms of cosine positive and add them together, you get exactly e to the x. So remembering them together, I just feel like is easier because they kind of go together. Now, something neat, which is not that important, but feels like I'd be committing a crime if I didn't tell you, is that you can see from these three formulas a very famous mathematical formula called Euler's formula, which you might have seen before. I'll tell you though. So Euler's formula does show up here. Euler's formula says the following. E to the I times theta, where I is the usual square root of -1, is equal to cosine of theta plus I times sine of theta. And it comes from well, one way to see it is it comes from exactly this, right? If you actually plug in, okay, we're gonna do it. It's no, it's not, it's fine. So I'm actually gonna write this out. So e to the I theta, this is actually a good example also of how when you're trying to find like a series for a more complicated thing, you can just use substitution. So instead of like actually doing the whole long process, I can say, well, e to the I theta is just gonna be this. It's going to be, and I'll try not to squeeze this in too tightly here. It's going to be the sum from n equals 0 to infinity of I theta to the nth power over n factorial. Well, check this out. That's going to be 1 plus I times theta over 1. I didn't write the 1 there, but I did. Plus I squared theta squared over 2 factorial plus I cubed theta cubed over 3 factorial plus I to the fourth theta to the fourth over 4 factorial. And we could go on for a ways here. Okay, here's what's neat though. What's I squared equal to? Well, I is the square root of -1, so I squared is equal to -1. In fact, let's write that over here. So I is the square root of -1. I squared is -1. I cubed is I squared times I, which is -1 times I, which is -I. And I to the fourth is -1 times -1, which is 1. And then the process repeats. So here's what's kind of cool about this. This ends up being, I'm going to group things together, 1. The I squared here is a -1, so I have a minus theta squared over 2 factorial. I to the fourth is a 1, so I have a plus theta to the fourth over 4 factorial. And if I'd written out more terms, my I to the sixth would be -1. So I'd have a negative theta to the sixth over 6 factorial, and so on. And then the odd terms, I'm going to factor out an I. So I'm going to get I times theta. And then here I have a I squared times theta cubed over 3 factorial, but the I squared is -1, so it's really minus theta cubed over 3 factorial, plus there would be an I to the fifth, which is just I times theta to the fifth over 5 factorial, and so on and so on and so on. But look, that's exactly cosine of theta, and that's exactly I times sine of theta. So kind of neat. Super important, not for this class, no, but a worthy relationship to observe. So here's 3 Taylor series we should know. I guess I should say Maclaurin series because they're all centered at 0, or at least the way we usually express them is by centering them at 0. And I would say there's a few more. So here's a few more. I'm trying to think which ones am I thinking of? Oh yeah, so a few more. We should definitely know that 1 over 1 minus x is equal to the sum of x to the n from n equals 0 to infinity, which is just your classic geometric series. 1 plus x squared plus x cubed, and so on and so on and so on. Here, the interval of convergence is not everywhere. So here, the interval of convergence is specifically -1 to 1 exclusive of any endpoints. Right? We know a geometric series only converges if your ratio is strictly between -1 and 1. Okay, now I forget I don't remember exactly the way we like to write the next one. I feel like I shouldn't tell you the wrong thing. So the next one is one of the natural logs. I honestly don't know which one the book typically has in it. Yeah. Does anybody know? Yeah, I was like, I feel like I should go look it up, but that seems terrible to do. Some natural log thing. So here's what I would point out. Yeah, it's probably the natural log of 1 plus x. That seems very likely. It might not be. It might be the natural log of 1 minus x. Either way, we can figure out what's going on here. So Here's what I would encourage you to think about. The derivative of this is 1 over 1 plus x. So I'm telling you right now, this is what I think you should know, and I don't even know it, right? I know that I can figure it out. I know that the derivative of this is that 1 over 1 plus x is 1 over 1 minus minus x. That looks a whole lot like that. That's going to be the sum from n equals 0 to infinity of negative x to the n, which is never a useful way to write, and never is a strong statement, James, which there's a better way to write that. I would prefer to write this as the sum from n equals 0 to infinity of negative 1 to the n times x to the n. The reason being that I know I have to undo this derivative to get back to the original expression. And integrating x to the n on its own is an easier process than integrating negative x to the nth power. I don't want to do a u substitution. So then we can say that the natural log of 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the n times the antiderivative of x to the n, which is x to the n plus 1 over n plus 1. So that's what that looks like. And if you want to write out the terms, my first term is going to be positive x to the 1 over 1 minus x to the second over 2 plus x cubed over 3 minus x to the fourth over 4, and on and on and on. I feel like there was one, oh yeah, there's one more stupid one that I really don't like. So yeah, what is this last one here? There's one that's like, oh, yeah, that's actually not, that one I like a lot. That's not, but yeah, so is that one we should know? Yeah, maybe, yeah, probably. Oh, I forgot to say here, the interval of convergence. So for this one, the interval of convergence, well, we're going to use the fact that differentiation and integration doesn't change the radius of convergence. So certainly for this function here, whose power series, whose Taylor series is this, we know the interval of convergence is from negative 1 to 1, right? Because it's 1 over 1 minus a thing. We know our thing, negative x, should be between negative 1 and 1. So that means x is between negative 1 and 1. Now, the only difference here is that either of those endpoints might not work out. So checking the endpoints, well, definitely negative 1 doesn't work. Because if you plug in negative 1, it's not in the domain of this original function. Also, if you plug in negative 1 here, you've got negative 1 to the n times negative 1 to the n plus 1, which is always negative 1. So just as a quick aside here, if you let x equal negative 1, you're going to get the sum from n equals 0 to infinity of negative 1 over n plus 1, which is essentially your harmonic series. It's the negative of it. You're missing a term, but it's essentially the harmonic series, which we know is divergent. It's the negative of the harmonic series, missing the first term. This diverges. On the other hand, if we plug in x equal to positive 1, we're going to get the sum from n equals 0 to infinity of negative 1 to the n over n plus 1. And that's essentially, actually, I should say you're not missing the first term here, right? You're starting at negative 1 over 1, which is not missing the first term. Still the negative, though. Here, this is your alternating harmonic series, which is convergent. This is convergent. So that means here our interval of convergence is exclusive of negative 1, inclusive of positive 1. All right, 2 more to go, one of which I really don't remember, so we'll figure out how to do it. But the 1 over 1 plus x squared is the fun one. So in a similar way, we can find, the arctangent of x. The arctangent of x. I don't know what the series for this is, but I know that if I differentiate that, the derivative of the arctangent of x is 1 over 1 plus x squared, which again, we're going to abuse this thing over here and say that's 1 over 1 minus negative x squared. I'll point out here that our interval of convergence is certainly going to be that negative x squared has to be between negative 1 and 1. which is going to amount to just x being between -1 and 1. So that means our interval of convergence for our other thing later, once we figure out what it is going to be the same, except we might have to include some of the endpoints depending on what's happening there. We'll figure it out. So that's, oh, I didn't write out what the series was yet. So for the derivative of arctangent, the series is going to be the sum from n equals 0 to infinity. And instead of saying negative x squared to the nth power, we're going to say it's -1 to the nth power times x squared to the nth power. Or a more sane person would probably write it as -1 to the n times x to the 2n. And just like last time, to find the function that we actually want to write the Maclaurin series for, we're going to integrate the derivative that we just found. So then the arctangent of x, Taylor series, Maclaurin. I know I keep saying the Taylor Maclaurin, they're the same thing, except you only get Maclaurin when it's centered at 0. And so far, all these have been centered at 0, so it hasn't been a problem. For arctangent of x, we're going to get the sum from n equals 0 to infinity of -1 to the n times x to the antiderivative of x to the 2n is x to the 2n plus 1 divided by 2n plus 1. If you want to write out some terms, we certainly can. It's going to equal, let's see, the first term is going to be x over 1, and then minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7. How bizarre. Like all these feel like just like, well, sure, that's what we get, but why? I don't know, because that's what we get. So interval of convergence. Let's just look at this and talk it out. Here's what you're really looking for most of the time if you're testing an endpoint. You're asking yourself, after I plug in this endpoint, is the thing I'm dealing with alternating or not? If it's not alternating, you're often going to get, well, you're just going to look at the thing and see, like, do I have a p-series that's invergent or convergent? Here, that's not going to be a problem, because here, when you plug in 1 to any power is 1, -1 to the n is still going to alternate back and forth between plus or minus 1. So we have essentially something that's similar to an alternating harmonic series, because our denominator is n to the first. So it's certainly going to converge when x is equal to 1. If x is equal to -1, it's still alternating, because -1 to the 2n plus 1 is always -1, because it's -1 to an odd power. -1 to an odd power is always -1. And this part's still going to alternate. So it's alternating either way, meaning we're going to get convergence in both cases because it's an alternating series, and the rest of the alternating series test is true. The sequence converges to 0, it's decreasing, and it's always positive from there. So here our interval of convergence is including the endpoint. So it's everything from -1 less than or equal to x less than or equal to 1, or written the more normal way, bracket -1 to 1. So there is a short list of series we should know. Question? Yeah. There's not a good rule. So the rule is we have to check the endpoints. That's really the rule, is that if it's limited in this way, and really we're kind of skipping a bunch of work here in that we are using the fact that this original thing, which is geometric, we know for a geometric series, you only get convergence if the ratio, right, the thing that's being subtracted down here, if that ratio is between -1 and 1. So we're kind of cheating it out. We're saying, okay, well, that has to be between -1 and 1, and then integration and differentiation don't affect the center and the radius of convergence. But the only thing that might be different is that the interval the endpoint, you might get convergence where you didn't before, or vice versa. Sure. No, I said a lot fast. I'll write it down because I know I was saying a lot. So for this one, here's what we're going to do. So let me back up for a second. Let's say we just started with this series, right? And no one told you where it came from. There's like, here's the series. Where does it converge? Well, if I wanted to figure out where it converged, what would I have to do? What do we usually do to find the interval convergence? What test do we use? Ratio test. So we're going to use the ratio test for this series. So for the sum from n equals 0 to infinity of negative 1 to the n, x to the 2m plus 1 over 2m plus 1, we're going to use the ratio test to determine the interval convergence. Now, I know that we don't really have to do this here, but I think it's good practice, and it'll show us kind of the usual process. So we're going to do the limit as n goes to infinity of the absolute value of, I think it is perfectly fine to ignore the -1 part, because -1 to the n plus 1 over -1 to the n is going to be -1. The absolute value is going to be +1. You don't need to write that part down, in my opinion. But you need to write down the rest. I'm going to see, ooh, this is good. So I'm going to have my an plus 1 here. So that's going to be x to the, be careful here. It's going to be 2n plus 3 because it's 2 times n plus 1 plus 1 divided by the same thing, 2n plus 3. On the bottom, it's going to be x to the 2n plus 1 divided by 2n plus 1. Yes, I know I did the thing I don't usually do, which is writing a fraction over a fraction. So then we would simplify this. Its limit as n goes to infinity of the absolute value of x to the 2n plus 3 divided by x to the 2n plus 1 times 2n plus 1 over 2n plus 3. This part simplifies to x squared. This part, the limit of that is going to go to 1. So we end up getting the absolute value of x squared. And we want that to be less than 1, which means x has to be between -1 and 1. Right? If x squared is less than 1, x can't be too positive, x can't be too negative. Now, you can write down some inequalities to figure it out, but I think it's pretty safe to say we know that if x squared is less than 1, we have to get that x is between 1 and -1. So here's what we know so far. This series, the sum from n equals 0 to infinity of -1 to the n of x to the 2n plus 1 over 2n plus 1 converges absolutely if x is between -1 and 1. We also know it diverges if x is bigger than 1 or x is more negative than -1. But, and here's the problem, we don't know what happens at the endpoints if x is equal to 1 or x is equal to -1. Because if x was equal to 1, the limit of this ratio test would be equal to 1. And that's inconclusive. If x is equal to -1, the limit of this ratio test would be equal to 1, and that's inconclusive. The endpoints of your interval always make the ratio test inconclusive because they're going to make it the limit equal to 1. And so we always have to test those. So we test them by just plugging them back into the original expression. So if we let x equal to 1, our series is going to become the sum from n equals 0 to infinity of -1 to the n times 1 to the 2n plus 1 over 2n plus 1, which normally you might just simplify that and write it as the sum from n equals 0 to infinity, -1 to the n over 2n plus 1. And this series converges by the alternating series test, which in my opinion, and again, this is my opinion, your instructor might feel differently, but in my opinion, when you're testing endpoints, I don't think you should have to go through the work of showing all the things have to be true for the alternating series test. It feels like you've already done so much work to get here. You can just say, yeah, I know that's going to work. I know that my non-alternating thing, 1 over 2n plus 1, right, my an equal to 1 over 2n plus 1, does the things it's supposed to. Its limit is 0, for sure. And it's certainly decreasing. an plus 1 is smaller than an. It checks out. It does all the things. So certainly this series, this Taylor series, does converge at that endpoint at x equal to 1. I will also point out it is conditionally convergent at that endpoint. Because if you look at the absolute value of this, you have something that's vaguely harmonic, right? It's 1 over n to the first. So we'll say more about that in a second. Similarly, if x equals -1, here's what often happens, which is not happening here. Most of the time, one of the endpoints makes your thing alternate, one of the endpoints does not. This is different than that. So usually, almost always, the one that makes it alternate, you get convergence. The one that makes it not alternate, you might get convergence, you might get divergence, depending on what you're dividing by. If we were dividing by n squared, we would get convergence. If we're dividing by n to the first, we're going to get divergence if it's not alternate. Here, though, if I plug in x equal to -1, look what we get. We get the sum from n equals 0 to infinity of -1 to the n times -1 to the 2n plus 1, all over 2n plus 1. That is still alternating. You can either justify this to yourself in one of two ways. You can either say -1 to the 2n plus 1 is always -1. So really you have -1 to the n plus 1. Or you can just straight up add those powers together and say you're going to have the sum from n equals 0 to infinity of -1 to the 3n plus 1 over 2n plus 1. Does that alternate signs? Well, better question. Does 3n plus 1 alternate parity? Does it go odd, even, odd, even, odd, even, or does it say odd, 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 or even, even, even? Well, if n equals 1, I get 4. If n equals 2, I get 7. Right? I'm adding 3 each time, so it better change even or oddness every time. So that's definitely going to alternate. So this also converges by the alternating series test. So here's what we're going to say. We're going to say that the interval of convergence is -1 to 1 with brackets. And if you're being asked, especially I think in web work, it's either web work or the other one, sometimes they ask you this really annoying question, which is, where is the series absolutely convergent? Where is it conditionally convergent? And where is it divergent? So we would say that this series is absolutely convergent from -1 exclusive to 1 exclusive. It's specifically conditionally convergent at exactly two values, -1 and 1. And it's divergent from -infinity to -1 exclusive union 1 to infinity. Which to me feels like overkill, but you can be asked that question. Usually, I'll point out, almost always the interval of conditional convergence is almost always either no points, 1 point, or 2 points. Right? It's either none of your endpoints, one of your endpoints, or both of your endpoints. But really, that's almost the only place your Taylor series or Maclaurin series or power series, those are the only places where you get conditional convergence, because the ratio test tells us that everything that makes the limit less than 1 gives you absolute convergence. All right. What's going on over here? Something weird's happening over here. Oh, okay, that's fine. All right. Okay, there's one other series I feel like I should mention, even though it's a terrible pain in the butt, mostly because I don't like it. I think I need to look it up. It's called the binomial series, I think. It's awful. Can I spell binomial? Binomial? Yeah. Oh yeah, it's that garbage. Okay, so binomial series. I don't think you'd have to memorize this one, but here it is anyway. So for the function f of x equal to 1 plus x to the kth power, where k can be any real number. Oh, sorry, you can't quite see that. Right? K is an element of the reals. So k could be a nice positive integer. That's never going to happen, because why would you want to find an infinite polynomial for a finite polynomial? You don't. But k could be something like 1/2 or 1/3 or a negative number. So lots of things here. So here's what you get. The Taylor series for this is 1 plus x to the k is equal to the following thing that's kind of terrible to write. It's 1 plus k times x plus k times k minus 1 over 2 times x squared, sorry, 2 factorial. And the pattern just kind of continues. The next term, you're going to just subtract one more thing from k. So it's going to be k times k minus 1 times k minus 2 divided by 3 factorial times x to the third. And it just continues on and on and on like this forever and ever and ever. There isn't really a nice, convenient way of writing it in the compact sigma notation. Or if there is, I'm not aware of it. And here, the interval of convergence is -1 to 1, exclusive of the endpoints. Interesting. Kind of. Okay, so that kind of begs the question, what can you do with all of this? That's a good question. I would say, so I'll be perfectly honest. I'm not real great with the what can you do with this. I just do math for the sake of doing math because I like doing math. But if you actually have to like use this stuff, you should talk to Duff. Duff knows like what you actually use math for, like physics or engineering things. But a couple things you can use this for are to estimate integrals that you couldn't otherwise calculate. Because some functions famously are not antidifferentiable, right? For example, I might say I would like to estimate the integral from 0 to 1 of e to the negative x squared. And e to the negative x squared doesn't have an antiderivative. Don't spend time looking for it. You won't find it. But we definitely could find a Maclaurin series or a Taylor series for e to the negative x squared really, really easily. Because we know that e to the x is equal to 1 plus x squared over 2 factorial, and so on and so on and so on. So e to the negative x squared, we're just going to take that x and replace it with negative x squared. So e to the negative x squared is going to be 1 plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial, and so on and so on and so on. And you can either make it look nicer by writing it like this, 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 6 factorial plus x to the 8th. Sorry, so I start making mistakes here. I made a mistake, right? X squared, x to the 4th over 2 factorial, x to the 6th over 3 factorial, x to the 8th over 4 factorial, and so on. But we could also just write it as the sum from n equals 0 to infinity of, instead of x to the n over n factorial, we have negative x squared to the n over n factorial, or preferably -1 to the n times x to the 2n over n factorial. So then we can use, so then here's where the questions get messy. Like, well, how many terms do I use? Well, that's where it's like, well, how many terms do we use? Sometimes they'll just tell you. Sometimes they'll say, let's use a 6th degree Taylor polynomial for e to the negative x squared to estimate this integral. So then we're just going to say, okay, cool. Well, the integral from 0 to 1 of e to the negative x squared, I'm just going to use terms until I get to the 6th power. Sometimes you don't get the power they want, right? Like they could have said use a 7th degree Taylor polynomial. They're like, well, I don't have up to the 7th power, so I'm going to stop at the power that's less than that. So here we're going to write that that's approximately given by the integral from 0 to 1 of 1 minus x squared plus x to the 4th over 2 factorial is equal to 2 minus x to the 6th over 3 factorial, which is equal to 6. And then you can just do the integral. So we're going to get x minus x cubed over 3 plus x to the 5th over 10 minus x to the 7th over 42, evaluated from 0 to 1, which ends up being 1 minus 1/3 plus 1/10 minus 1 over 42. No one should spend time simplifying that. It still feels like we're kind of like not doing anything really. So a better question, which I hate to ask because it's a pain, but the better question here is, how good is our estimate? What's our error? That is where I have to remember some stuff that I don't like remembering, but fine. So the idea here is that, well, I need to go back and rethink about this. So here's what you should really be doing. We're going to instead, let's write the Taylor polynomial for the integral from 0 to x of e to the negative y squared. Okay, so, and again, this is where I have to like make sure I'm doing the right thing because it's easy to make mistakes here. So easy enough, he says confidently. E to the negative y squared, we know what that is. It's going to be the sum from n equals 0 to infinity of, we just wrote it over here. Let me go look back at my notes. E to the negative x squared was negative 1 to the n, x, except I'm using y now, y to the 2n over n factorial. Don't forget the dx. And then the great thing about this, dx, dy. The great thing about integrating a sum is you can pass it through and you only have to deal with the part that's like the variable. So this is really going to be the same as the sum from n equals 0 to infinity of negative 1 to the n over n factorial times the integral of y to the 2n dy. Bless you. Then we integrate, we get the sum from n equals 0 to infinity of negative 1 to the n over n factorial times y to the 2n plus 1 over 2n plus 1. I forgot the very important limits of integration here. Evaluated from 0 to x. And then if we plug those in, it usually works out very nicely that we get negative 1 to the n over n factorial times x to the 2n plus 1 over 2n plus 1 minus 0, right? If you plug in 0, you get minus 0. So what we can say now is that the integral from 0 to x of e to the negative y squared dy is equal to, I'm just going to write some terms here. Let's see, x over 1 minus, we'll have to be extra careful because it's n factorial here, x cubed over 1 times 3 plus x to the 5th over 2 factorial times 5 minus x to the 7th over 3 factorial times 7, and so on and so on and so on. Okay. So now coming back to the question I was trying to ask, how do we know how good our estimate is? Well, if we plug in 1 for x, the integral from 0 to 1 of e to the negative y squared dy is going to equal 1 minus 1 over 3 plus 1 over 10 minus 1 over 42. I should have written the next term. The next term was going to be plus x to the 9th over 4 factorial times 9. So it's going to be 1 over 4 factorial times 9 minus something plus something. And there's your remainder. And since this series is alternating, the remainder is always bounded by the first term of the remainder. So we can say that our estimate is as good as being off by at most 1 over 4 factorial times 9. So our error here is less than or equal to 1 over 4 factorial times 9, which is something. I don't know, 24 times 9 is 216. So our estimate is as good as being at most off by 1 over 216. That's not too bad in the world of integrals. I mean, I'm sure a computer could do better. It also feels kind of silly to do any of this because like a lot of this aspect of it is like, well, we have computers and calculators that can estimate these things much more quickly and accurately than we can estimate. But this is kind of the idea of where some of that came from. That's how we are actually estimating integrals, is by doing something like this. Probably not actually, but I pretend it is. Okay, so let me see something real quick here. Yeah, that's fine. Something else we often like to do with this, and kind of getting back to more the point I was, not the point, but knowing these series makes it really easy to come up with something else. So someone might ask you something like, sure, find, for example, the limit as x approaches 0 of, sure. So I'm trying to think of the one I like. That's fine, sure. X minus sine of x divided by x cubed. Without using L'Hopital's rule. And you might be thinking, well, what does this have to do with anything we just talked about? Well, the idea here is that we can write a Taylor series for this expression, specifically using the Taylor series for sine. So I find it easy just to write out the whole term. So I'm going to say, well, neat. X minus sine x over x cubed. I'm going to write as 1 over x cubed times x minus the expansion of sine of x. And again, sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so on and so on. Well, great. Let's simplify this now. So x minus all of that, the x's cancel, and we've got 1 over x cubed times negative negative is positive x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, and so on and so on and so on. And then if we multiply through the 1 over x cubed, we're going to get 1 over 3 factorial minus x squared over 5 factorial plus x to the 4th over 7 factorial, and so on and so on and so on. So then we can say that the limit as x approaches 0 of x minus sine x over x cubed is equal to the limit as x approaches 0 of this expression, where every term except for the first term has some power of x. Right? And so if we let x go to 0, that's going to go to 0, that's going to go to 0, and we're going to end up with 1 over 6. Does that seem crazy? I don't know. Is it right? Let's check. Let's use L'Hopital's rule. So if we actually did this the way a more rational person would do it, using L'Hopital's rule, x minus sine x over x cubed. First of all, just to double check, we do actually need to use L'Hopital's rule if we're going to do this way, because it is a 0 over 0 type of limit. So using L'Hopital's rule, we get the limit as x approaches 0 of the derivative of the top, which is 1 minus cosine of x, divided by the derivative of the bottom, which is 3x squared. Still a 0 over 0 type because cosine of 0 is equal to 1. So we use L'Hopital's rule again. We get the limit as x approaches 0 of the derivative of the top, which is 0 minus cosine of x, minus sine of x, so sine of x over 6x. Still a 0 over 0 type, so we use L'Hopital's rule again. And at that stage, we're finally going to get the limit as x goes to 0 of cosine of x over 6, which is cosine of 0 over 6, which is 1 over 6. So yeah, it's 1 over 6. Kind of neat. It's really, I think it's actually really neat that you can do this, but again, I have a hard time, obviously, finding the usefulness of this. There is usefulness, I just don't know it very well. So you should ask someone else about, not that I'm not like saying don't ask me. I just don't have very good examples of like why this is important or how you use it in the future. But it definitely is. I know it gets used for lots of things. I just don't do that. So yeah. The other thing I should mention, and I know we only have 5 minutes left here, but the error part is the part I wish I could avoid talking about because I just find it really kind of tedious and difficult to deal with, but it is important. So it's nice that an alternating series, the error is really easy to calculate. So in fact, let's mention that again. So if we have an alternating series, say like the sum from n equals 0 to infinity of -1 to the n times some a sub n, which just looks like a sub 1 minus a sub 2 plus a sub 3, and so on and so on and so on. It's going to be true that if we want to approximate, or if we estimate this infinite sum with a partial sum, say Sn, here's what happens. The infinite sum from n equals 0 to infinity of -1 to the n times an, we get the partial sum, so we get a1 minus a2 plus a3 minus a4 plus all the way to some capital Nth term. That's your partial sum. And then you have the rest. You have an plus 1 minus an plus 2 plus an plus 3. I'm ignoring the fact that you have to deal with whether it's a plus or a minus. It doesn't really matter that much. But all this over here, this is your Rn, your remainder after the first n terms. And if it's alternating, we are in luck, because for an alternating series like this, it is true that this remainder, which is all these terms added together, that remainder in absolute value is always, always, always less than or equal to the absolute value of that first term, a sub n plus 1, of the remainder, which is lovely, beautiful. We like it a lot. But you know what? Not every series is alternating. And you might like to know how good your estimate is for a non-alternating series. And that is much less nice. So typically, here's how this goes. So if we have a non-alternating series, and we estimate the infinite sum with a partial sum, again, Sn, here's the deal. So same kind of idea in that you have this infinite sum from n equals whatever to infinity of your sequence. So you're going to get your first however many terms, a1 plus a2 plus all the way to a sub n, and that's your nth partial sum. And then you have your remainder, which is no longer alternating. And the question is, how do we estimate or bound that remainder? And I'm going to throw it at you really fast because we're almost out of time, but I feel like I can't just leave you with not saying it. It seems like it'd be terrible. So here's the idea. This remainder, this Rn, yeah, sure, R capital N, as a function of x, because usually there's some x in there that we're plugging into this thing, right? It's a power series typically. It's going to be, in fact, I should have, yeah. I should have maybe written this in the more typical way. Yeah. Sorry, that's, I apologize. So I owe you I owe you more time. So what I should have written here was the usual kind of Taylor series expansion instead of just, so let me write this real quick. If you need to leave, I get it. But if you can hang out for a minute, let me just write this so that I don't feel like I've totally done you dirty. So the usual Taylor series thing, um, yeah, sure. So we usually have that, and then we expand this out to your Sn, which is going to be, f of c plus f prime of c times x minus c, plus all the way to the nth term, which looks like that. Fn, sorry, this is really gross looking, James. And then you have your remainder over here, which is starting at the n plus first derivative at c divided by n plus 1 factorial times x minus c to the n plus 1, plus all the other terms. Okay, so here's what we get to say. And I know, again, I'm speaking through this, but here's the deal. The remainder after those first n terms is actually equal to the n plus 1 derivative evaluated at sum a divided by n plus 1 factorial times x minus c to the n plus 1, where a lives between c and x. And then the idea is that we don't know what that a is. So what we're going to do is we're going to then find a way to bound this. That's the idea for dealing with the remainder for a non-alternating series, power series, is we say, okay, well, the rest of the stuff, we don't know exactly, or there's a thing that is exactly equal to that we don't know, but we can definitely figure out something that is bigger than that, which will bound your error.